and I thank organizer to giving me opportunity of the talk. The polyhedral realization in the title is one of combinatorial description of crystal base, and crystal base is a powerful tool to study representations of quantum groups over the algebras, so which is appearing in the talk of Toshiki yesterday, and crystal is appearing in the talk of Volkas today. The goal of this talk is we will give some explicit forms of polyhedral realizations for crystal base of affine quantum groups in terms of extended Young diagrams. So first 3 sections, we will give some explanation for this terminology, and in the 4th section, we give some main result. So first, we consider quantum groups, and we briefly explain the history of real algebras and their representations. So let G be a vector space over C. So real algebra means it is some vector space over C with Lie bracket product. So this product satisfies these 2 axioms. So first, the product of x and x equals 0, and it satisfies this identity, so-called Jacobi rule. So first, we give a quick explanation for finite dimensional simple real algebras, and after we explain their variations. So first, we consider this one. So since G has some structures and Lie bracket product structure, so we can regard G as ring. So we can consider the notion of ideal. So this simple means G has no ideal other than 0 and G. So for example, if G is SL2 of C, so it is a vector space of 2 times 2 matrices whose trace equals 0. Then this is naturally vector space, and defining bracket product as this one, xy minus yx, then this G becomes real algebra, and this is also simple. And putting E, F, H like these matrices, then these are generators of G. So generator means all elements in G can be expressed by these 3 elements combining by sum and the scalar product and Lie bracket product. And among these generators, these relations hold. And in general, the following theorem holds. So when G is finite dimensional simple real algebra, then G has generators denoted by EI, FI, and HI, and I is in index set I, and which satisfies these 6 relations. And here, this AD means ADXY equals bracket product X and Y. And this AIJ is an element of matrix called Cartan matrix. And this G satisfies only these 6 relations essentially. So essentially means all relations between EI, FI, HI can be obtained by combining these 6 relations. And this Cartan matrix satisfies these 3 conditions. The diagonal elements equals 2, and other elements are non-positive. And if Aij equals 0, then Aj equals 0. And this matrix Aij is symmetrizable. So that is, there is some diagonal matrix D such that dA is symmetric, and this dA is positive definite. So it is natural problem how many matrices satisfy these 3 conditions. The matrices satisfy these 3 conditions are classified by diagrams called thinking diagrams. So these are list of all thinking diagrams, and each diagram represents some matrix. The rule for the correspondence between matrix and diagram is as follows. If I and J is connected by single edge, which means Aij equals Aji equals 1 minus 1. And if they are connected by arrows with double edges, which means Aij equals -1 and Aji equals -2. And if it is triple edges, it means Aij equals -1 and Aji equals -3. And if I and J are not connected, then Aij equals Aji equals 0. So combining this fact and this theorem, finite dimensional simple real algebra are classified by thinking diagrams. So in this way, the structure and classification of complex finite dimensional simple real algebras are well known. And the structure and the classification of finite dimensional irreducible representation of finite dimensional simple real algebras are also well known, as you know. So in this way, the theory of finite dimensional simple real algebras are quite successful. So if we can consider natural variations of finite dimensional simple real algebras, it can be expected to obtain some new interesting theories. So under this philosophy, some variations are considered. The first one is affine real algebra. So recall that when G is finite dimensional simple real algebra, it is classified Cartan matrix satisfying these three relations. So in particular, in the third relation, third condition, Aij is symmetrizable and dA is positive definite. So if we can change this positive definite to non-negative definite, then we get affine real algebra. And there is another variation called quantization, and we get quantum group. And considering the two variations, affinization and quantization, then we get affine quantum groups. So after we will explain these two objects, first we consider affine real algebra. So as I said, let us take a matrix satisfying these three conditions. The first and second conditions are same as in the finite dimensional simple real algebra case. The third condition is changed. The matrix Aij is symmetrizable and the symmetric matrix dA is non-negative definite and not positive definite. And it is a natural problem how many matrices satisfying these three conditions, and it is classified by called affine thinking diagrams. So there are 14 kinds of affine thinking diagrams. So I partially wrote the diagram explicitly like this. So in this way, the matrices are classified by affine thinking diagrams. And to define affine real algebra, we need a preparation. So let H be a I+1 dimensional vector space over C, and we assume that Hi and D is a base of H. And we take alpha I in dual space of H for each I, such that alpha j of Hi equals Aij, so which is element of affine Cartan matrix, and alpha j of D equals delta 1j. And now we can define affine real algebra. So let G be a real algebra with generators Ei, Fi, Hi, and D, such that for two elements H and H prime in H, these six relations hold. And note that if this H and H prime equals generator Hi and Hj, then these six conditions coincide with the relations in finite dimensional simple real algebra. So we can understand affine real algebra is obtained from finite dimensional simple real algebra by changing Cartan matrix to non-negative definite one, except for the new generator D. And in the theory of abstract algebra, there is some procedure such that from formal symbols like this and formal relations between them, so we can formally define some algebra. So following the procedure, we can define affine real algebra. So unlike finite dimensional simple real algebra, these affine real algebras become infinite dimensional one, and all non-trivial representations become infinite dimensional. And as so there are several applications of affine real algebra for Q series, number theory, physics, and so on. So for example, using affine real algebra, another proof of Jacobi triple product formula are given, and another proof for Roger-Ramanujan identities are given. And now the variations of Roger-Ramanujan identities are well studied, and there is another application for physics like three-wave lattice model. And this is affine real algebra, and there are another direction of variation called quantum groups. So roughly speaking, it is a similar algebra to G. So let Q be indeterminate, and let RQ factorial, and MRQ be these rational function of Q. So when Q equals 1, Q approaches 1, RQ approaches to integer R, and this guy approaches to R factorial, and this guy's approach to binomial coefficients. And let G be finite dimensional simple real algebra. And let Yuki of K be C of Q algebra with unit 1 with generators EI, FI, and Q of H satisfying these 6 relations. So from forward symbols EI, FI, and Q of H and relations between them, we can formally define the algebra called Yuki of K, and it is called a quantum group associated with Q. So comparing with the algebraic structure of original real algebra, they have similar generators and they satisfy similar relations. And there is some operation like Q approaches to 1. And applying this operation, we get relations of universal enveloping algebra of K from these 6 relations. So this is quantization. And we can consider both variations, affinization and quantization. So let A equal Aij and vector space H and alpha I, just as in the definition of affine real algebras. That is, we take them like this. So in particular, Aij satisfies A is symmetrizable and dA is non-negative definite but positive definite. And H is I plus 1 dimensional vector space with base Hi and D. So just as in the finite dimensional case, we can define Uq of K. So let that is, Uq of K is C of Q algebra with unit 1 and with generators EI, FI, and Q of H, and H runs this set, satisfying these 6 relations. So except for the new generator Q of D, these relations are completely the same as the previous relations of quantum group associated with finite dimensional simple real algebra. So we can understand affine quantum group is obtained from classical quantum group by changing Cartan matrix to non-negative definite one. Okay, so this is affine quantum group. So today, I'd like to consider the representation of affine quantum group Uq of K. So let P be the set of lambda in H star such that lambda of Hi and lambda of D are integer, and it is called weight lattice. And let P plus be the subset of B such that lambda of Hi and lambda of D are non-negative. And there is a fact that for each lambda in P plus, there exists a representation denoted by V of lambda, such that there exists some small v lambda, and EI v lambda equals 0 for all I, and v lambda is simultaneous eigenvector for Q of H, and eigenvector is Q of lambda of H, and v of lambda is generated by small v lambda under the action of F. So that is, it is generated by the vector in the form fj1 dot dot fjr v lam as C of Q vector space. And note that this representation V of lambda is an analog of finite dimensional irreducible representation L of lambda of finite dimensional simple real algebra. So there is a fact that the finite dimensional irreducible representation of finite dimensional simple real algebra are classified by P plus, and the representation parameterized by lambda has the structure as follows. So there is some small l lambda, and EI lambda equals 0 for all I, and this is a simultaneous eigenvector for action of H, and L of lambda is generated by small l lambda. So in this way, today we only consider the representation V of lambda, so which is some analog of finite dimensional irreducible representation. Okay, and the extended Young diagrams in the title are introduced for combinatorial study of representation V of lambda. So it is defined as the infinite sequence of integers yk, such that each yk is integer, and this sequence is weakly increasing, and there exists some integer y infinity, such that this sequence converges to y infinity. So, for example, if we take a sequence of integers -3, -2, -1, -1, 0, 1, then this sequence is weakly increasing and it converges to y infinity equals 1. And each extended Young diagram is expressed as Young diagram drawn on the quarter plane like this. So for example, since y0 equals minus 3, we draw the horizontal line y equals minus 3 between x equals 0 and x equals 1, like this. And next, since y1 equals minus 2, so we draw the horizontal line y equals minus 2 between x equals 1 and x equals 2. So repeating this argument, we can draw several horizontal lines like this. And finally, we connect them by vertical line, so we get some Young diagram. So in this way, each extended Young diagram can be drawn like this. And we named each corner as concave corners or convex corners. The corners drawn by red red are called concave corner. That is, the corners making by going up and going right is called concave corners. And the corners making by going right and going up is called convex corners. And each integer point, including concave corners and convex corners, are coloring by index set I. So we define a map from index set to index set I as identical map and extend it to a map pi a of 1 from z to I by periodicity n. So each integer point ij is colored by index set I by pi a of 1 of I plus j. So these notions like extended Young diagrams and corners and colorings are originally introduced by these authors for the combinatorial study of affine quantum group. So I will explain the background of these terminologies. So let f of lambda k be vector space over Q of Q, having all extended Young diagrams with y infinity equals k as base. So if Gay's affine type, like named these four, the vector space f of lambda k is the Yuki of Gay modules, and submodule of f of lambda k generated by phi k is isomorphic to v of lambda k. So this is one main object of this talk. Here, this phi k is extended Young diagrams kkk, so that is extended Young diagram without boxes. And so for almost all k. And lambda k is called fundamental weight. And roughly speaking, in their study, so the action of FM, so which is one generator of real quantum groups, and is as follows. So acting FM on base extended Young diagram T, then a concave corner ij coloring by M will be changed to convex corner. So that is, the concave corner ij in T will become to convex corner like this. So this is the action of Fm on f of lambda k. So in this way, we can combinatorially treat the representation v of lambda k of affine quantum group by using extended Young diagram and corners and coloring. But today, we will treat these objects, extended Young diagram, corners, and coloring for another purpose, that is explicit description of polyhedral realization of crystal base. So let G be finite dimensional simple real algebra or affine real algebra. And recall that for each lambda in P plus, there exists some representation v of lambda of Yuki of Gay such that there exists some small element, small v lambda, and it satisfies EI v lambda equals 0, and this v lambda is simultaneous eigenvector for Q of H, and v of lambda is generated by small v lambda. And now we give some property of crystal base. Today we will not explain the definition of crystal base v of lambda. We just explain the properties of them. So first, v of lambda is a set with maps called Kashiwara operators and denoted by EI tilde, FI tilde. So it is a map from v of lambda to v of lambda cap 0, and this 0 is some extra element of v of lambda. And these are considered as the combinatorial analogs of action of EI and FI on representation of v of lambda. And there exists some element v lambda bar in B of lambda such that B of lambda is a set of elements in the form fj1 tilde fjk tilde v lambda bar. And note that this element might become 0, so we remove the element 0. And as a property of B of lambda, it holds the number of elements in B of lambda coincide with the dimension of original representation V of lambda. And there is a map from weight from B of lambda to weight lattice P, such that the value of Hi on weight of this element of crystal base coincide with the eigenvalue of original element fj1 fjk v lambda in V of lambda. So this is the generator of original representation. So for Q of Hi. So in this way, by studying crystal base B of lambda, we can know the eigenvalues of V of lambda or dimension of V of lambda. And we can also know the structure of tensor product of V of lambda and so on. So in this way, so if we can know the structure of V of lambda, we can get the important information of V of lambda. But by using only the definition of crystal base B of lambda, it is difficult to know this important information. To do that, some combinatorial descriptions are useful. So today, so B of lambda has a bunch of combinatorial descriptions, but today we consider the polyhedral realizations which describe B of lambda in terms of infinite integer vectors. So to define these polyhedral realizations, we need to fix some sequence iota equal I1, I2, from I equal 1 to n. So now we define Z infinity iota of lambda as a set of infinite sequence of integers a1, a2, which converges to 0. So of course this set does not depend on iota and lambda, but one can define maps denoted by fi tilde, ei tilde, and weight on Z infinity iota of lambda. And this definition of maps will depend on iota and lambda. So now I wrote the definition of three maps, weight, and ei tilde and fi tilde here, but I will not explain the detail of them. The essential point of these three maps are as follows. Above ei tilde, fi tilde, and weight are defined by only sum of integers. So in particular, in this definition, we didn't use the representation theory. So if even if we don't know the representation theory, we can calculate the maps ei tilde, fi tilde, and weight on Z infinity iota of lambda following these rules. So these three maps on Z infinity iota of lambda are very computable one. And there is an injective map from B of lambda to Z infinity iota of lambda, and it is denoted by psi iota of lambda, such that the V lambda bar in B of lambda goes to 0, 0, 0, in Z infinity of lambda. And this map commutes with ei tilde, fi tilde, and preserves weight. So recall that these three maps are defined on B of lambda, and these three maps are also defined on Z infinity of the lambda. So this theorem says this map is compatible under these three maps. So since this is compatible, by this theorem, we can reduce the calculations of three maps on B of lambda, which are important for studying the representation V of lambda, to three maps ei tilde, fi tilde, weight on Z infinity iota of lambda, which are very computable. And unfortunately, this map is not surjective, so we define the image of this map, and we call it polyhedral realization for B of lambda. So let us see some example. We take K as SL3 of 3, and let lambda be the element in P plus such that lambda of HI equals 2 and lambda of H2 equals 0. So recall that B of lambda can be written like this. So that is, it is generated by V lambda bar. So there is some element V lambda bar, and applying casual operator F1 tilde and F2 tilde, we get the graph of crystal base. And we get this graph. But in fact, drawing this graph is difficult because we need representation theory. If we try to draw this graph by only the definition of crystal base. And as by the property of crystal base, we can know the dimension of V of lambda equals 6 because this crystal base has 6 elements. It coincides with dimension of representation. And this is the graph of polyhedral realization. V lambda bar goes to the element 0, 0, 0, and applying casual operator F1 tilde, we get this diagram. So, following the rules written in here, we can draw this graph without representation theory. So here, this each vector A1, A2, A3 implies A1, A2, A3, 0, 0, da, da, da. So each element represents some element in Z infinity of lambda. So in this way, we can draw the graph of polyhedral realization. And note that these 6 vectors coincide with the set of integer points A1, A2, A3 satisfying these inequalities. So in fact, these 3 vectors satisfy these inequalities, and conversely, the integer vector A1, A2, A3 satisfying these conditions will appear in this diagram. So that is, these 6 vectors coincide with the integer point in this gray triangle. So some interesting phenomena happens considering realization of crystal base, which is representation theoretical object. Then some geometrical object polytope is appearing, and this phenomena holds for more general algebra. So it is natural problem to find the explicit form of this polytope, like as these red inequalities. And several researchers tackled these questions. So in case of Gauss finite dimensional simple real algebra, so then if iota is this specific sequence, then some explicit form is given. And in our previous study, if Gauss type A, B, C, D and iota is cyclic one, then some inequalities of explicit forms are described in terms of column tableaus. And so Rittelmann considered this problem in the context of string con or string polytopes. When iota is iota satisfies nice decomposition, so which is uniquely determined for each type of finite dimensional simple real algebra, then some explicit form of string polytopes are given. So note that this polytope is different from our polytope, but these are dual polytope in certain sense of crystal theory. And Glaser-Postnikov and Koshiboy-Schumann found if iota is any sequence and iota is Gauss type A, then some explicit form of our polytopes and S iota of lambda are given by using some combinatorial object called wiring diagrams or line crossings. So in case of Gauss affine real algebra, then for specific sequence 1 to data n, 1 to data n, then some explicit form of this polytope is given. And in this talk, we'd like to consider the case Gauss affine real algebra of type A upper 1n. And iota is some cyclic one. And we'd like to describe the explicit form of polytopes by using extended Young diagrams I explained before. And I'll remark that we already obtained similar result for other 3 types, D upper 2, C upper 1, or A upper 2. But for simplicity, today we only consider the case Gauss of type A upper 1n. So we'd like to consider this problem. So as notation, we fix some notation. So we take I1 data n such that it is some permutation of 1 to data n. And we only consider the sequence iota cyclic one. That is, it repeats the sequence I1, I2, in infinite many times. And we define some homomorphism xk from z infinity to z, such that xk of a1, a2, equals ak. So it is like coordinate function. And we identify the set of positive integers and direct product of set of positive integer and I, such that 1, 2, n, n plus 1, 2n, are identified with y 1, I1, 1, I2, 1, in, 2, I1, 2, I2, 2, in, and so on. So in this way, depending on the sequence iota, we identify these two sets. So for example, if iota is 3, 1, 2, 3, 1, 2, 3, 1, 2, then each coordinate function x1, x2, x3, will identified with double indexed one, x1, 3, x1, 1, x1, 2, x2, 3, x1, x2, 2, and so on. And for two index ij with I is not equal to 0, then we define Pij as 1 or 0 following if the fixed pattern I1, I2, in, I is appearing earlier than j, then we define Pij as 1. And if not, we define Pij as 0. And by using this small p, we define the capital P, k, of t like this for each index k. So first, we set pk of k as 0, and we inductively define as pk of t like this by using small p and coloring pi a of 1. And for each integer point ij and parameter s and k, we put lsk of ij as this coordinate function. The left index is a bit complicated, but the right index is just coloring of integer point ij. And this is a key definition for our main result. For each extended Young diagram T with y infinity equal k, we assign a homomorphism LSK iota of T like this. So that is, for concave corner P in T, we consider the sum of LSK of B defined here with coefficient plus 1. And as for convex corners P in T, we consider the sum of LSK of P with coefficient minus 1. So in this way, for each extended Young diagram, we can assign some homomorphism like this. And these homomorphisms will be inequalities defining polyhedral realization. And let EYDK be the set of extended Young diagrams with y infinity equal k for k, and let conv iota of infinity be the set of all homomorphism LSK iota of t assigned for all extended Young diagram T. And parameter s and k runs all positive integer and index I. And finally, we define the box Rk as this homomorphism and the box R tilde of k like this homomorphism. And let the conv k iota of lambda be the set like this, corresponding to the relation between 1k and pi a of 1k plus 1 or pi a1 of k minus 1. So note that. So now we define these two sets. Now we identify these two sets, and of course, in this set, there is some natural order like this. So by importing this natural order, we can consider natural order of this set of direct product. And so on. So by this natural ordering, by this natural ordering, we can consider the these conditions. So if y1k is smaller than 1 pi a upper 1 of k plus 1 and k minus 1, then this set is a set with single element like this. And 1k is greater than k plus 1 and k minus 1, then it is a set of homomorphism assigned for all extended Young diagram EYDK except for phi k. Here, this phi k is an extended Young diagram without boxes. And if not, this set becomes a set of boxes defined here. So now we can give the explicit form of polyhedral realization. So let K be of type A upper 1. Then the polyhedral realization is described like this. So that is, it coincides with the set of A in Z infinity such that phi of A is non-negative for all phi in conv iota of infinity and conv k iota of lambda. So recall that this conv iota of infinity is a set of homomorphisms corresponding to all extended Young diagram, and this second set is defined by extended Young diagrams or boxes. So in this way, inequalities defining polyhedral realization are expressed by combinatorial objects such as extended Young diagrams and boxes. So this is my main result. So let us see some example. We consider the case gates of type A upper 1 and k equals 1 and iota equals 2, 1, 3, 2, 1, 3, So let us calculate several inequalities defining polyhedral realizations. So to do that, we take these easy extended Young diagrams. So let us calculate homomorphisms corresponding to these diagrams. So first, this is easiest extended Young diagram, so which has one concave corner and does not have convex corner. So following the definition of LS1 iota, we consider the LS1 corresponding to this concave corner. So it is equal to XS1. So next we consider T1. So it has two concave corners, 0, 0 and 1, 1. So we consider the sum of LS1 with coefficient plus 1. And it has a single convex corner, so we consider the sum of LS1 with coefficient minus 1. So following the definition, we get this homomorphism. So calculating similarly, we get homomorphism corresponding to T2 and T3, like this. So let us calculate the inequalities corresponding to conv lambda. So since iota is 2, 1, 3, 2, 1, 3, so we get this ordering. So following the definition of conv lambda, we have conv 2 iota of lambda has a single element minus x1, 2 plus lambda of 82. So conv 1 iota of lambda is a set of boxes R1 plus lambda of H1. So we can compute explicitly the boxes 2, 3, 4, 5, 6 like this. And finally, let us compute conv 3 iota of lambda. So which is the set of homomorphism assigned for all extended Young diagrams except for phi 3. So we take easy extended Young diagrams except for phi 3. So we take these three objects. So following the definition of L0 3 iota, we get corresponding homomorphism like this. So we get partially get inequalities defining polyhedral realization. So for example, considering this xs1 is non-negative, is appearing here, and this xs plus 1, 2 plus xs3 minus xs plus 1, 1 is non-negative, is appearing here. And considering similarly, this guy is non-negative and this guy is non-negative, are appearing here. And considering for conv lambda. So for example, minus x12 plus lambda 82 is non-negative. We get this homomorphism. So considering similarly for these guys and these guys, we get rested inequalities. So in this way, we can combinatorially describe the inequalities defining polyhedral realization. Okay, that's all. Thank you very much.
Questions? You said so you had in type CN and for are those the types you have issues with? The one with the I don't know, like the fork at the end of the affine the Dinkin diagram?
Yes. So for example, yes, for example, if we consider the upper two case, then I'm sorry. Yeah. So if we consider another type, we change the coloring here. Yeah, and it is already defined by these authors. So for considering another type, we use another coloring. Yes.
Yes, but you like 3, right? On in the finite ones.
Yes. So these authors define the coloring for only these 4 types. Yes. So yeah, we only get these 4 type. Yes. So we only get the result for these 4 types.
Why? What's missing for the other types?
Yes. For other types, I'm working on. Yes, but I will use another combinatorial object called Young walls, defined by Kang, and it is valid for all classical affine types. So we will use it. Thank you.
A question? I have questions.
Yes.
You consider here like Coxeter, so your sequence like you take Coxeter word and it's periodically continue. So if it does take not Coxeter, power of Coxeter, but some R-reduced decomposition, so, and then continues periodically, so does it work?
You mean the
sequence here.
So it's arbitrary one?
Yes, we consider, for example, the reduced decomposition of A.
Yes.
And then continue its periodically.
Yeah, so in that case, my result doesn't work. We only, it works for like cyclic one. Yeah, cyclic one or adapted one, yes.
More questions? Thank you again, Yuki.
Thank you.